Hello, and thank you for your interest in our work titled Sim-to-Real Causal Transfer, a metric learning approach to causally-aware interaction representations. Understanding and predicting human trajectories is a critical challenge in robotics and autonomous systems. While current models can predict paths very accurately, they often lack a deep understanding of the underlying causal relationships driving agents and behaviors. This becomes especially important in multi-agent settings where interactions are complex. An influential benchmark in this space is Causal Agents by Waymo. It aims to assess robustness in motion forecasting through causal relationships. They manually labeled agents in the driving scenario as causal and non-causal agents, like the image on the left with causal agents marked with red circles. A causal agent is defined as an agent influencing the path of the equation. Causal agents benchmark showed that by removing the non-causal agents from the scene, the output of the predictor changes, which is undesirable, as seen on the image on the right, where the removal of non-causal agents has led to a higher mean ADE. However, the Waymo work overlooks a crucial aspect: indirect causal agents. These are cases where an agent influences the outcome through a chain of interactions. On the left, we show an example. The elderly pedestrian in red causes the green pedestrian to reroute upwards, which in turn forces our ego agent to slow down. If the red pedestrian weren't there, the green would proceed straight, and the ego agent wouldn't need to adjust their pace. Another limitation of Waymo's evaluation is how it handles agent removal. Although agents are labeled as non-causal individually, the benchmark removes all of them at once. At first glance, this might seem harmless, but in reality, removing multiple non-causal agents simultaneously can still influence the ego agent's behavior. This is illustrated in the figure on the right, where we see that removing more than one supposedly non-causal agent can, in fact, lead to a change in the ego agent's trajectory. Because of these limitations, we ask, how well do current models capture causal interactions? Our study reveals that although some models are resilient to removing non-causal agents, they struggle significantly when causal and especially indirect causal agents are removed. This insight motivated us to create a diagnostic dataset and method to address these gaps. We built a diagnostic dataset grounded in the well-known ORCA framework, which simulates reciprocal multi-agent interactions. This dataset allows us to systematically analyze how well models understand the causal structure of interactions between agents. Through counterfactual simulations, we calculated ground truth causal effects of each agent removal and labeled agents into three categories: non-causal, direct causal, and indirect causal agents. We also proposed a metric called average causal error, in short ACE, measuring the difference between the predicted and ground truth causal effects, where lower numbers indicate higher causal understanding of models. Here, we show that current models can often withstand the removal of non-causal agents as marked by the low ACE and C numbers. However, their predictions degrade significantly when causal agents are removed. This reveals a clear weakness in causal understanding, particularly in recognizing indirect causal influences. To improve causal understanding of models, we propose two causal regularizers based on different granularity of causal labels. We first calculate the embeddings of the factual and counterfactual scenarios by passing them through the scene encoder of the prediction model. The first regularizer uses contrastive plus to pull the embeddings of the factual and counterfactual scenarios together when a non-causal agent is removed and push the ones of causal agents away. The intuition behind this method is that by removing non-causal agents from the scene does not change a lot in the eyes of the ego agent, so the embedding of it should be close to that of the factual scenario. However, the removal of causal agents should change the representation. This regularizer uses binary causal and non-causal labels. But thanks to the simulator, we have more fine-grained causal labels, which are the causal effects. Therefore, the second regularizer uses these more fine-grained causal labels to rank the agents and enforces this ranking in the distances in the latent space. We show that using this methodology is indeed useful for decreasing the average causal error and increasing causal understanding of the models. This improvement is even more pronounced when using the more fine-grained causal labels in the ranking regularizer. An interesting benefit of having higher causal understanding is the higher out-of-distribution performance, as shown in the first figure quantitatively and in the other two figures qualitatively. All the previous results were conducted on our synthetic dataset, but how can we translate these findings to real-world scenarios? We propose a simple multitask learning approach where the predictor is trained on the real-world data using a prediction task, and our causal regularizers are used on the synthetic data at the same time. We show that our ranking regularizer improves real-world performance in two datasets, ETH-UCY and NBA. This improvement is even more pronounced in low data regimes, like when using 25% of the data in ETH-UCY. Interestingly, when using 25% of the data, the addition of our ranking regularizer to the baseline achieves the same performance of using 100% of the data, which shows our causal labels help in sample efficiency. To summarize, in this work we did an analysis of causal understanding of recent prediction models and proposed two regularizers to improve any model's causal understanding, which we showed translates into better performance in out-of-distribution scenarios. We also proposed a sim-to-real causal transfer approach, which we demonstrated helps model performance and sample efficiency. Importantly, this can be achieved without requiring costly real-world annotations. Thank you for your attention.